It is still snowing outside on this lovely snowy snow day, and the cat is bored and he is back. He wants to know more about polynomial functions. So open up your book to page 348 and let's begin. All right, right away in the beginning, you start with polynomial functions in one variable, and they give you this lovely long list of a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, etc. And then they do some definition things down here with a, where a sub n does not equal 0 and are real numbers, and n is a non-negative integer. What I want to point out here is just some examples of what they're saying about a polynomial is and a polynomial is not. So we've got that our coefficients are real numbers. That means something like 3x to the fourth plus 2x minus 1 could be a polynomial. What is not a polynomial then? A coefficient with an imaginary number. So if you have 3i x minus 2i x squared, that is not a polynomial. Notice it doesn't say that you have to have a rational number coefficient. You could have the square root of 3x squared plus 2x because those are real number coefficients. And now let's talk about the exponents. The exponents have to be non-negative integers. For instance, our 4 here and our 1. Or you can even have x to the 21st plus x to the 134th. But what you cannot have is x to the negative 1, which translates into 1 over x. You can also not have x to the 1/2 because that means the square root of x. Neither of those qualify as a polynomial. Also, what do they mean by a sub n cannot equal 0? That means the very first coefficient cannot equal 0, or the largest coefficient on the largest degreed term. Why is that? Because if your leading coefficient is 0, then you just don't have a term there, which makes no sense. All right, let's move on. Example 1. Before we begin example 1, I would really like you to take a look at A and at C. On number A, we have a polynomial like we normally write it. Notice we usually start with the largest exponent on our variable, which is a 5 in this case, then 4, then 2, then 1, then 0. I would like you to compare that with C. Notice on C, it's not listed that way. This exponent is 4, 3, 8, and 1. The reason I'm pointing this out is that the degree of the polynomial is the same as the term with the highest degree within that polynomial. The first term has degree 5, second term has degree 3, degree 2, degree 1, and degree 0. The degree of polynomial A is 5, and the leading coefficient is the number that is being multiplied by that variable, in this case 8. Don't always assume it will be the first term in line. For instance, like C. C is also degree 8, but the leading coefficient is negative 4, even though it's the third term in. Placement doesn't matter as far as the degree and the leading coefficient goes. For B, it is not a polynomial in in one variable because the middle term has both x and y. That's all I have to say about that. So please Pause the video and do the check your progress. Here are the answers to check your progress. 1a is not a polynomial in one variable because of the very last term, which is 4 over x. X has the exponent of -1, and so it eliminates that from being a polynomial in 1 degree. Here are the answers to 1b and 1c, and we are ready to move on. All right, real world example 2. Before you begin this example, notice something is a mistake in the book. They say refer to the beginning of this lesson and find the volume in the air in the lungs 2 seconds into the respiratory cycle. If you look at the equation that is next to the picture of the baby, this one that I'm moving around right here, you are going to see that it's not quite the same as the one that they use in the lesson. The numbers on this example are slightly different. They've taken them out to the nearest thousands instead of the nearest hundreds. When you go to do your check your progress, use the one that's in the example. So we're actually just going to move this and cover it right up. Don't use that other equation that's by the baby. Just use the one that's here in the example. Now they give you the example because what they want you to realize is that you do exponents first. So you are putting the 2 in, you are cubing the 2. Then you take that result and multiply it by that coefficient. Again, squaring the 2, multiplying by the coefficient, and then just 2 to the first power multiplied by the coefficient. Then you find your sum. So remember your order of operations. Go ahead and try the check your progress using the equation in the example. Pause the video and then check your answer. The answer to check your progress 2 was 0.7332 liters. I hope that you got it correct, and let's move on. Example 3 is the kind of examples that when algebra teachers look at it, they get all excited and start to drool because they know that this is the perfect kind of problem to throw on a non-calculator page to have students do tons of algebra to see if they're paying attention and know what they're doing. So, that being said, let's see what's going on. They're asking for f of 3, c minus 4, subtract 5 times f of c, and here you're applying it to this function x squared plus 2x minus 3. Remember that when you say f of x, and then you say f of c, and you say f of 3c minus 4, those are the variable or variable groups that you are substituting in for x. So first of all, f of 3c minus 4 means putting 3c minus 4 in where the x goes, in both places where the x goes. Then also remembering that the first one is being FOILed. So you have to FOIL the first one because you're squaring it. Then you use the distributive property on the second one. And this gives you f of 3c minus 4, which is the first part of this equation, right here. Once you have that answer, you have to subtract 5 multiplied by what you get when you take f of c. So you're taking f of c here, you're putting c in for x, so that's c squared plus 2c minus 3, and then you're multiplying that whole equation by 5 using the distributive property on it. So you get 5c squared plus 10c minus 15. You put that all together and you take your first answer. This was from the first part. This was the f of 3c minus 4. And now you are subtracting the results from the second part. Subtracting is always good because students forget to take that negative sign to each of those terms. That's how they get the negative 5c squared minus 10c plus 15. And you combine your like terms to get your final answer. This is mostly an algebraic exercise, requires focus. Try the check your progress. Good luck. These are the answers to the check your progress 3A and 3B. Okay, when you're ready, let's turn the page. On the next page, we have graphs of polynomial functions, and the key thing to remember here is that the word maximum. It says the general shapes of graphs of several polynomial functions show the maximum number of times the graph of each function may intersect the x-axis. Now, what do they mean, the maximum number of times? We just got off of a whole chapter studying quadratic functions of degree 2, all right? Now, we know that the maximum number of times a quadratic can cross the axis is twice, but we also know it can cross it once. That's supposed to be intersecting. That'll be, there we go, it's intersecting, say that. So it can cross it exactly once, or it can cross it not at all and have imaginary roots. But if it crosses it, the most it can cross is twice. Same thing, function of degree 3 down here, the cubic function. It could be crossing 3 times, but what if it was raised up a little bit? It might only cross once. Again, a quartic function, which means 4, degree 4. It could be down, but if it were raised up, it could be hitting it not at all. And the same thing, of course, with number 5, something like that. It could just be crossing it once or twice, or excuse me, yeah, once or twice, or once or 3 times or 5 times. There we go. All right, and that's all I have to say about that. Let's move to the next big box. This is the key concept box of end behavior of a polynomial. What they want you to realize is that end behavior means literally what is happening at the ends of the parabola. If you have an even degreed function, it comes from above and it returns to above. If it starts up, it ends up. Same thing down here. If it starts down, it ends down, just like the parabola, because it's even. This means as x approaches negative infinity, so in other words, as I'm going to the left, my function is going up to positive infinity. This part means as I'm going to the right, towards positive infinity, but I have to stay on my parabola, the function f of x is going up. Positive infinity, when you're talking about f of x, means up. Positive infinity, when you're talking about x, means to the right. Remember that f of x is always also another way to say y. So in the box below it, it's saying as you move to the left, as x moves to the left, the y value is going down. So as you move to the left, the y value is going down. As you move to the right, the y value is going down. And this is true for even functions. That's why even functions can have 0 real roots, because they never have to technically cross the x-axis, which is not true for an odd degreed function. If you have an odd degreed function, your end behavior starts down, and then it always goes, in the end, in the opposite direction. No matter how many squiggles there might be in between, you might be coming like this, but eventually you have to end up going down if you are an odd degreed function. Again, this means as x moves to the left, y is going down. As x moves to the right, y is going up. So that's end behavior, what is happening at the ends of the function. Take a look at it, think about it, but that's all I have to say. On the next page, the key concept, zeros of even and odd degree functions, is trying to say the odd degree function will always have an odd number of real zeros. that means there will always be at least one odd real zero if you have an odd function, because it has to cross the axis at least once. Even ones, even degree functions will always have an even number of real zeros or no real zeros at all, because it doesn't have to touch the x-axis. An odd degreed function always has to touch the x-axis, so it always has at least one. Example 4. Describe the end behavior of each of these functions. Determine whether it represents an odd or an even degreed polynomial function, and state the number of real zeros. I think the last two are the easiest. For A, you have two real zeros. It is going down, so it has to be an even degreed polynomial. This one is up on one end, down on the other, so it has to be an odd degree polynomial, and there are 1, 2, 3, 4, 5 real zeros. Now what about the end behavior? They're saying y goes to negative infinity as x goes to the left. Y goes to negative infinity as x goes to the right. Now remember, when we're saying going to the right, we are going to the right. However, you have to stay on your function as you're going to the right. That's why you go to the right. As you go to the right, you're also going down. On this next one, f of x is going to positive infinity as x goes to the left. So as we go to the left, we are at the end headed towards positive infinity. It doesn't matter that we took this little detour down. And then as f of x, or y, goes to negative infinity as x goes to the right. So as we go to the right, we are again at the end going down. All right, try the check your progress. Here are the answers to the check your progress 4A and 4B. I hope that you're understanding. That is it for this lesson. Make sure that you also read between the examples and wrote down the definitions of vocabulary words. See ya later. Bye-bye.